Shreyash, is it visible to you?
Yes, ma'am.
Okay.
अब नहीं है मैम.
अब नहीं. हाँ, okay. एक बार ट्राई कर रही थी बस. Okay. Now the screen is visible. Shreyash?
Yes, ma'am.
Okay. Now let us continue. Yesterday I have done 2 corrections. Maybe this slide I have done the correction. Maybe you can note it down. Below this temperature, formation of carbon dioxide is more favorable, while above this temperature, formation of carbon monoxide is more favorable. So at high temperature, carbon function as reducing agent, and at low temperature, carbon monoxide. This correction we have done. Let us come to the question. Okay. First question is, although thermodynamically feasible in practice, magnesium is not used for the reduction of alumina in the metallurgy of aluminium. Why? So this is the question. It is also very important. It is related to the Ellingham diagram even. But without that, we can explain this in a different way. So aluminium can reduce magnesium oxide. Okay. Thermodynamically feasible in practice, but it is not used for the reduction of alumina. Alumina means what? Alumina means aluminium oxide. Okay, aluminium oxide. Now, aluminium can reduce magnesium oxide at high temperature near about 1350 degrees Celsius. So in Ellingham diagram, you can see that at this particular temperature range in Ellingham diagram, that means the line for magnesium to magnesium oxide, that formation line lies above the line of aluminium oxide. You can see the Ellingham diagram. Only at this particular temperature, 1350 degrees Celsius. Okay, and above this temperature. This indicates that in this temperature range, aluminium oxide is more stable than magnesium oxide. Okay, this is also related to Ellingham diagram. Aluminium oxide is more stable than magnesium oxide. So if one compound is more stable than the other compound, the delta G value would be negative. So delta G value would be negative, means the reaction will be possible, or that means the reaction is feasible. So this is the answer of the question. I'll repeat. Aluminium can reduce magnesium oxide at high temperature, that is above 1350 degrees Celsius, because at this temperature range in Ellingham diagram, line for magnesium oxide lies above line for aluminium oxide. This indicates that in this temperature range, aluminium oxide is more stable than magnesium oxide. And delta G naught value for the reaction. What is the reaction? Aluminium plus magnesium oxide, Al plus MgO gives aluminium oxide and magnesium. Al2O3 plus Mg. It would be negative. Delta G value for this reaction should be negative. This is the answer of the first question. Okay, so it is related to Elinghart diagram. No need to remember exact Elinghart diagram, but you have to remember this particular concept related to Elinghart diagram. Okay, now we will come to the next question. Suggest a condition under which aluminium could reduce magnesium oxide. Suggest a condition. Okay, so what is the condition? The condition means the temperature must be at a particular range. So at that particular range, the temperature must be high. It should be 2000 Kelvin. It is near about that, very high temperature. At this temperature only, aluminium could reduce magnesium oxide. And the last question is, why is reduction of metal oxide easier if the metal formed is in liquid state at the temperature of reduction? Okay. So in this question, we can correlate entropy concept and states of matter. The entropy of liquid metal is more than entropy of metal in the solid state, because metals are exist in the solid state. One exception is there. What is the exception? Which metal is the exception? Mercury is the only exception which exists in the liquid form. Rest of the metals under normal condition exist in the solid form only. So entropy of liquid metal, that means molten state of metal, is more than entropy of the metal in solid state. The value of delta S for the reduction process is more on positive side when the metal formed is in the liquid state. So that means entropy is positive when the metal is in the liquid form. Therefore, the value of delta G for the reduction process become more negative side and the reaction become probable or easier. According to Gibbs-Helmholtz equation, delta G equal to delta H minus T delta S. If delta S is higher and the temperature is also higher, then there is the possibility of high negative value for delta G. So if the value of delta G is negative, the reaction is feasible. So this is all about the answers of the questions. Okay, so this is all about related to PPT. Now we will directly, so if any problem is there, any doubt is there, I will clear at the end of the session, or I will send the answer through WhatsApp group. Okay, as you wish. Now I am stop sharing. So I am coming back. Okay, now let us continue with our next topic, extraction of iron. So I know yesterday we have completed extraction of iron. Uh, that is industrial method of extraction. Industrial method of extraction we have completed. So we have seen the big plant and all. So today we will discuss the points which are related to extraction of iron. Okay. For that, let us think about another important tool. So that means I will give another important tool where extraction of iron is explained. Data edge class we will discuss in that. It will take 1 minute, okay? Sriyesh, the screen is visible? Sriyesh? Sriyesh?
Yes, ma'am, visible.
Visible, okay. Thank you.
Welcome.
Very good.
Extraction of iron.
Sriyesh, now screen is visible?
Yes, ma'am.
Okay. Maybe little bit disturbance in the audibility of the slide will be there. So it will take it to, maybe it will be exceed only half second only. So we can solve that. Let us hope for the
Iron
best.
is mined from the Earth's crust in its combined state as an ore. It needs to be extracted from its ore before it can be used commercially. Let us see how iron is extracted from its ore. The extraction of iron from its ore is a three-stage process.
This you can note it down. Extraction of iron. It will be in three different stage. Three stages are there in the extraction of iron, and the stages are concentration. First, second stage. Major stages are explained here. Okay. Stage 1, concentration of the ore. Stage 2, calcination, and stage 3, smelting. Okay. Note down these points. Simultaneously, I am also writing on a copy so that I can make out how much time it will take to write. Okay.
In this lab, you will be taken through the steps of iron extraction. Let us start right away. Note, iron extraction takes place at high temperatures, and hence, all personnel wear protective equipment to keep safe from potential hazards. Iron is mainly extracted from its principal ore, hematite. Ore obtained from the mine contains gangue, which largely consists of silica and earthly impurities.
This you can mention. Okay. Major impurities present in hematite along with iron ore. Silica and earthy impurities. Okay. This is important. Silica and earthly impurities.
The light earthly impurities are removed in the first stage of extraction, concentration. Let us see how this happens. First, powdered ore is added into the hydraulic classifier.
So here you can write the name of the process. Concentration of iron ore can be done through hydraulic washing. Mention the point. Hydraulic washing is also known under the name levigation. 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 Okay. This is the instrument, hydraulic classifier.
Click the powdered ore to add it to the classifier. A jet of water is passed through the bottom of the reservoir. This thoroughly mixes the content. The lighter gangue particles move up and are washed away from the top. The denser particles of the ore settle at the base and are collected via an outlet. The concentrated ore still has volatile impurities in it, so it has to be processed further. It is taken for calcination, which is the second stage in the extraction process.
I hope first stage is clear to everyone. Okay. Is it clear to everyone? Poonam? Poonam?
Yes, ma'am.
Okay. So now we will move to the next stage.
The second stage of iron extraction takes place in a reverberatory furnace.
This you have to be noted down. Okay. Second stage is calcination. Remember the process. Along with that, you have to mention the name of apparatus. Calcination is done in reverberatory furnace. Reverberatory furnace. And which are the important parts of a reverberatory furnace? Have a look. Inlet for concentrated ore. A. B is hearth or furnace. And second is coal. It is a fuel. D is blast of flame. and E is outlet for volatile gas. Because significance for calcination process is volatile impurity is expelled out as well as moisture is also expelled. Okay.
Concentrated ore is poured onto the hearth of a reverberatory furnace. Click the concentrated ore to add it to the furnace. The burning coal present in the furnace increases the temperature inside. The ore is subjected to this high temperature in a limited supply of air. As the ore gets heated sufficiently, moisture and volatile oxides from the ore evaporate and the ore becomes porous. The resulting calcined ore is now ready for the third stage, smelting.
Now second stage is over. We have the product calcined ore.
Smelting is carried out in a blast furnace. The blast furnace is a tall structure and can be divided into zones depending.
So you can mention the process melting and the name of the apparatus blast furnace. Yesterday we have seen the actual plant and here it is a bisection only. Look at the different zones: reduction zone, slag zone, fusion zone and combustion zone. No need of remembering the temperature, but you can remember which zone is of highest temperature and which is the lowest temperature one, that you can mention.
On the temperature and the reactions that take place in each zone. The calcined ore collected from the reverberatory furnace is mixed with coke and limestone in the ratio 8:4:1.
This you have to be noted. The ratio between the components of charge on the blast furnace. 8:4:1. Calcined ore, coke and limestone. In the ratio 8:4:1. That is important.
This mixture is called the charge. The charge is poured into the furnace from the top through the cup and cone arrangement. Click the charge to feed the furnace. A preheated blast of air is sent into the furnace from the bottom. This air is at a high pressure and at an extremely high temperature of 1500 degrees Celsius. At this temperature, coke, which acts as a fuel, burns and produces carbon dioxide in the combustion zone.
So you can mention the equation. Combustion zone, reaction taking place is C plus O2 giving CO2, coke plus oxygen giving carbon dioxide, and it is highly exothermic reaction. It is a highly exothermic reaction. Okay. Equation is important. C plus O2 giving CO2 and the reaction is highly exothermic. Carbon dioxide is a gas which is moving up.
The carbon dioxide formed moves up the furnace and reacts with more coke, thus getting reduced to carbon monoxide.
This is the second equation that you have to note down. Carbon dioxide react with coke, forming another compound carbon monoxide, CO2 plus C giving carbon monoxide. Remember the equation. And this particular reaction takes place in the second zone and it is called fusion zone. Okay. So two gases are obtained here, carbon dioxide and carbon monoxide. Carbon dioxide is in combustion zone and carbon monoxide is in fusion zone. Okay.
This, being an endothermic reaction, reduces the temperature to 1200 degrees Celsius.
Second reaction is endothermic reaction. Endothermic.
The carbon monoxide formed in the combustion zone rises to the reduction zone at the top of the furnace. The temperature in this zone is 400 to 700 degrees Celsius. Carbon monoxide reduces the iron oxides in the ore to iron at this temperature.
So you can mention all the equations, okay? Fe2O3 is ore, calcium ore, reacts with the carbon monoxide. Here the role of carbon monoxide is reducing agent, resulting iron and carboxyl. And FeO, it is also present along with the compound there, which reacts with the carbon monoxide forming iron carbon dioxide. Fe3O4, small quantity is also associated with there. It also gets converted into iron, molten iron, or spongy iron it is. Okay.
Iron formed at this temperature is in its solid form and is called sponge iron. The sponge iron moves down and melts in the fusion zone and slowly sinks to the bottom. This molten iron has some dissolved impurities. Meanwhile, the limestone present in the charge decomposes to give calcium oxide.
Next reaction, calcium carbonate. Calcium carbonate function as a flux. It decomposes at high temperature, forms calcium oxide and carbon dioxide. Mention the equation.
Calcium oxide reacts with silicon impurities.
Second equation, slag formation. Calcium oxide reacts with SiO2. Silicon dioxide is formed as a, it is there along with the charge as an impurity. It is an acidic impurity. Calcium oxide react with silicon dioxide forming calcium silicate slag. Okay, calcium silicate CaSiO3.
In the ore to form the slag, calcium silicate in the slag zone. This molten slag sinks to the bottom of the furnace. Being molten iron. Iron are then cut from different outlets at the bottom of the furnace. Volatile impurities form hot waste gases and are removed through an outlet at the top of the furnace. The molten iron obtained is called pig iron. It is solidified in sand balls and comes into various shapes. Most blast furnaces continue to operate continuously for 10 years once commissioned, with only periodic shutdowns for maintenance purposes.
So this is all about extraction of iron. Now let us move to the next extraction, extraction of copper. Okay. Write down the heading, extraction of copper. One minute. It is coming.
The extraction of copper. Copper exists in its native ores, copper pyrite,
The name of all the ores: potassium, copperland, Cu2S, copper pyrite is CuFeS2, cuprite, copper oxide, in fact, this oxide, malachite, it is a combined ore of copper hydroxide and copper carbonate. Okay. Sriyesh, screen is
Yes,
clear?
ma'am. Yes, ma'am.
Okay. Thank you.
The extraction of pure copper is a 5-step process. This includes concentration, smelting, polymerization, and refining.
These are the 5 stages of extraction of copper: concentration, roasting, smelting, polymerization, and refining. Okay, note down these 5 stages: concentration, roasting, smelting, polymerization, and refining.
Click any process to learn more about it. Copper is mainly extracted from its principal ore, copper pyrites.
This is the major ore of copper and it is copper pyrite. Okay, so in this particular slide, we are seeing all the processes associated with extraction of copper from copper pyrite. Okay.
Copper pyrites contain many siliceous impurities called gangue. To remove these, the ore is first crushed and then ground to a fine size. Being a sulfide ore, it is concentrated by the froth flotation process.
Name of the process you have to mention: concentration done through froth flotation process, because it is a sulfide ore. Okay.
Flotation tank contains water, to which collectors such as pine oil and stabilizers such as
Mention these 3 important substances associated: water, pine oil, and aniline. The role of pine oil we know, and aniline also we know.
aniline are added. The pulver ore is then added to this tank. A rotating paddle called the agitator mixes the contents in the tank. Compressed air is blown, in which froth is created in the mixture. The ore particles are wetted by pine oil and rise to the top in the froth. The impurities get wetted by water, become heavy, and settle at the bottom. They are removed periodically through an outlet. The froth is skimmed off to a settling tank. The concentrated ore settles at the bottom. It is then removed and dried. This concentrated ore still has some volatile impurities in it. Hence, it is taken for roasting, which is the second step in the extraction process. The second step of copper extraction is called roasting. It is carried out in a reverberatory furnace. The concentrated ore is placed in the furnace. It is subjected to a high temperature with a limited supply of air. Here, the copper pyrites get oxidized to form copper 1 sulfide and iron 2 sulfide.
Write down this equation. This is the equation related to roasting process. CuFeS2 balanced equation. 2FeS2 CuFeS2 plus O2 gives Cu2S plus 2FeS plus SO2. Along with SO2, you can show an upward arrow. is also important. Copper sulfide and sulfide. Equation important. And name of the apparatus done in reverberatory furnace. And this equation associated with the process.
Large amounts of sulfur, which are present as an impurity, also get oxidized to form sulfur dioxide. Copper 1 sulfide and iron 2 sulfide get further partially oxidized to form copper 1 oxide and iron 2 oxide.
Whenever equation is coming on the screen, try to write down the equation, okay? This is the second and third equation related to the same process. Cu2S plus 3O2 giving 2Cu2O plus SO2, and second is FeS plus O2 giving FeO plus SO. So we have two major products. One is copper 1 oxide, cuprous oxide, and second is ferrous oxide. Along with that, one more byproduct is there, sulfur dioxide.
Respectively. Other impurities such as arsenic and antimony form volatile oxides. The roasted ore is now ready for the next step, smelting. Smelting is carried out in a blast furnace. The modern blast furnace is water jacketed throughout. It is made up of steel and is lined by refractory bricks. It has outlets for waste gases at the top. A mixture of roasted ore, sand and coke is...
Write down this charge. Roasted ore plus coke plus sand. In the previous case, instead of sand, limestone was there. And here sand is there. Because sand is it has the role of flux. And sand is a flux which is acidic in nature. And the reason is the impurities associated with the ore is basic in nature. That is FeO, iron oxide. Ferrous oxide is basic in nature. That's why here we are using an acidic flux. Okay?
Is dropped into the furnace through a cup and cone arrangement. The mixture is heated strongly, while hot air is simultaneously pumped in through pipes called tuyeres. The reactions that started during roasting take place here too, and oxides of iron and copper are formed. Most of the iron 2 oxide combines with silica or silicon dioxide.
First two equations I think we have done, and write the third equation. FeO plus SiO2 giving FeSiO3. It is the slag. Ferrous silicate. The name of the slag is ferrous silicate. Iron oxide is a basic impurity. SiO2 is acidic flux, and FeSiO3 is slag.
And gets converted to form iron silicate. This is called slag. The copper 1 oxide that is formed recombines with iron 2 sulfide to form copper 1 sulfide and iron 2 oxide again. Therefore, to prevent this reaction, it is very important to remove all the iron impurities. Now, the molten material contains sulfides of copper 1 ions and iron 2 ions along with sand and coke. This is called matte. The slag and matte are removed from different outlets.
Here you can write one important point, matte. M-A-T-T-E. This is the name of the product obtained after smelting. M-A-T-T-E. And what is the composition of matte? Composition of matte is, it is the mixture of two major compounds. One is Cu2S, cuprous sulfide, and the second one is ferrous sulfide, FeS. Okay. These are the two components, major components present in matte. I hope it is clear to you. Sriyesh?
Yes, ma'am.
Noted the point. Matte important. Okay. MaTe and composition Cu2S plus FeS.
The copper matte or coarse metal is now ready for the fourth step, Bessemerization. The molten matte produced during smelting is transferred to a Bessemer converter. A blast of hot air is blown into it through the tuyeres. Once again, the remaining iron 2 sulfide gets oxidized to form iron 2 oxide. This in turn combines with sand to form slag. In this way, all the iron is removed. Copper 1 sulfide forms copper 1 oxide. Since there is no iron left, it reacts.
Note down the equations related to Bessemerization process. Why is it called Bessemerization? Because name of the apparatus is Bessemer converter. That's why the process is called Bessemerization. Note down the equations. FeS plus O2 giving FeO plus SO2 and FeO plus SiO2 giving FeSiO3, Cu2S plus O2 giving Cu2O plus SO2, last one Cu2S plus 2 Cu2O giving Cu plus SO2. Okay.
With copper 1 sulfide and forms copper. The molten mass is allowed to cool. The dissolved sulfur dioxide gas slowly escapes. This gives a blister-like appearance to the solid copper. Therefore, at this stage, it is called blister copper.
Note down this name, blister copper. This is the name of the product obtained after Bessemerization process. Why is it called blister copper? Because sulfur dioxide escape from the molten substance. Because of the escape of SO2, bubbles are formed at the surface. That's it appears as blisters. That's why the product is called the blister copper.
The blister copper still has some impurities and has to be further refined in order to get pure copper.
Okay. This is all about Bessemerization, and the last process is known to you. Refining is done through electrolytic refining. Okay. So this is all about the process extraction of copper. Okay. Now I am stop sharing. I am coming back.